Welcome to This Explainer. Let's jump right into something that is, honestly, completely mind-bending. We're going to explore how basic mathematical foundations actually build the most intricate, complex systems you can possibly imagine. I am so excited to share this with you today because we're looking at the secret geometric engines running right beneath the surface of reality.
So here's the core paradox for you. How on earth do you code infinite complexity? I mean, how do you build something endless using nothing more than basic math and a simple XY grid? For centuries, mathematicians looked at infinity as this untouchable, abstract philosophical thing. You definitely couldn't just bottle it up in a simple spatial formula. And yet, looking at modern computational approaches, we are doing exactly that. It feels like it shouldn't be possible, but it is literally the basis for both cutting-edge artificial intelligence and fundamental physics. We are actively taking the infinite and grounding it on a finite grid. Let's run through our roadmap for this explainer real quick. 1. Simple rules, complex patterns. 2. Functions over Cartesian space. 3. CPPNs, growing neural networks. 4. Tiling, geometry of probability. 5. Comparing the two approaches. And finally 6. The universe of computation.
Okay, kicking things off with Section 1. Simple rules, complex patterns. The engine of creation.
We have to start by acknowledging a huge fundamental truth explored by thinkers like Stephen Wolfram, and it's this. Massive complexity doesn't actually require a complex beginning. If you just apply basic repetitive rules over space, you can get these incredibly intricate, non-random patterns that echo the very fabric of reality itself. Just picture a simple cellular automaton, right? Just a single black square on a grid. If you give it a super basic rule for how to interact with the squares around it, it doesn't just fade into static. Because of this continuous feedback loop, where each new state perfectly dictates the next, it feeds on its own output. And boom, it generates a nested, highly complicated, pseudo-random structure. It proves without a doubt that simple math rules, applied consistently, can drive universe-level complexity.
Moving on to Section 2. Functions over Cartesian space, the shared canvas.
To really wrap our heads around the two case studies we're looking at today, we first need to define the shared engine that makes them both possible, Cartesian space. Now, the crucial thing to remember here is that these coordinates are not just boring points on a static high school geometry map. Now, they are highly dynamic canvases just waiting for instructions. Think about biology. A developing cell knows exactly where it is, like front, back, left, or right, entirely based on chemical gradients. It's basically reading its physical coordinates. Well, in our computational world, we can set up that exact same coordinate space and manipulate it purely through math. We are quite literally giving life to empty grids.
By layering functions on top of this space, we can warp the geometry and compose entirely new forms. We define the axis representing space, we apply symmetric mathematical gradients, and then we layer periodic functions to build structure. This specific framework, function composition over coordinate Cartesian space, is the absolute magic wand here, and it brings us perfectly to our first creator.
Which brings us to Section 3, CPPNs, growing neural networks, Kenneth Stanley's approach.
So Kenneth Stanley takes direct inspiration from biology and uses what he calls compositional pattern-producing networks, or CPPNs for short. Look at how this works. By combining a symmetric function with a periodic one, you get distinct segments with opposite polarities. It behaves so much like a biological embryo developing. You get this amazing property of repetition with variation. Just think about the fingers on your own hand right now. They repeat a core structural concept, right? But they vary slightly in length, width, and position. By applying this simple function composition over spatial coordinates, the artificial network naturally grows structural patterns with all those varying local details. It completely bypasses the need for us to manually hardcode every single connection.
Stanley translates simple 2D spatial geometry into incredibly complex neural network architectures through a really elegant pipeline. First, you define your 2D spatial coordinates as chemical gradients. Second, you pass them through a CPPN to compose those specific geometric patterns. And finally, you project that into four-dimensional space to map out the actual neural connectivity. Using this method, a basic grid of Cartesian coordinates blossoms into a vast, highly optimized artificial intelligence architecture. He is literally painting AI from geometry.
Let's dive into Section 4, tiling, geometry of probability. Kyle McLean Smith's approach.
Now, Kyle McLean-Smith uses the exact same spatial coordinate system, but instead of AI, he applies powers and metallic means to create probability tiles and intricate spiral tilings. He takes rectangles, applies scale symmetry, and mathematically draws out the decay of probability as an iterative geometric series moving toward a vanishing point. It is a stunning visual representation. Every single tile represents a very real probabilistic outcome, twisting endlessly into a spiral that gets closer and closer to infinity without ever actually reaching it.
Let's make this super concrete. Think about the number 7. Just imagine you have a statement that is false 9 out of 10 times. Okay, so how many times do you have to make that statement to cross a 50% probability threshold of it being true just once? Smith calculates this visually by whittling down geometric tiles. He repeatedly multiplies the base tile by a scale symmetry of 9 over 10, and mathematically, on exactly the 7th iteration, the visual geometry crosses that halfway probability threshold. It is almost spooky how perfectly continuous probability translates directly into physical Cartesian space.
Bringing it all together in Section 5, comparing the two approaches, two sides of the same coin.
We've got Kenneth Stanley, who composes gradients over space to generate complex neural network structures, heavily inspired by biological embryogeny. And on the flip side, we have Kyle McLean-Smith, who composes probability tiles and spiral tilings to map continuous probability and non-halting decay, relying on pure geometry. But here is the beautiful secret. The underlying engine for both is absolutely identical. It is mathematical function composition over Cartesian space. Whether you're generating AI architectures or mapping geometric decay toward a vanishing point, you are using the exact same basic tools. Two completely different outputs grown from the exact same mathematical soil.
And that leads us to our final stop, Section 6, the universe of computation, tying it all together.
Smith actually connects these concepts right back to Stephen Wolfram's foundational theories of physics. In fact, he discussed computational irreducibility directly with Wolfram. Smith notes the precise relationship between computational limits, causal edges, and energy in the universe. He points out that these mathematical limits, these spatial points at infinity, might directly correlate to how energy and physical limits function in the real world. It's a brilliant way of tying highly abstract mathematical concepts back to the raw physical mechanics of the cosmos.
I want to leave you with this final thought from this explainer, perfectly encapsulated in Smith's quote here. Physics seems to explain non-halting is fundamental. Think about that. If such infinite complexity, from biological neural networks all the way to the geometric decay of probability, can naturally grow from simple spatial math and Cartesian coordinates, is our entire universe just a beautiful non-halting computation waiting to be understood? What other universal secrets are hiding in simple geometric grids? Keep wondering and keep exploring.